I worked on developing absorbers for terahertz spectroscopy in the physics department under Marylou. So one prominent area of terahertz spectroscopy in our lab is something called electron spin resonance. This sort of study investigates the unpaired electron spins in a solid or liquid in order to learn more about the structure of that solid or liquid. For example, in biology, we can study the structures of protein complexes. This right here is a proteorhodopsin hexamer, which is a protein that responds to light. But outside of that, we're not too sure about its function. So in order to learn more about its function, hopefully we can learn more about its structure, and that will elucidate its function. So a little bit about the physics behind electron spin resonance. What you have are electrons that can be spin up or spin down in your solid or liquid. And then we take a high-powered light source and shine it down at our electron. So if you have one that is spin up in our magnetic field, we take the light source and that causes it to tip, and then it precesses, and then we are looking at it precessing all the way back to its upright position. So ESR at UCSB is very unique because we have something called a free electron laser, which can give us power at up to 100,000 times greater than a typical ESR experiment. For example, we can get up to 1 kilowatt of power, whereas in an experiment maybe at another university, they can get 10 milliwatts. So with high power, we also have high frequencies. We can get 100 gigahertz to 3 terahertz. And in order to match these high power and frequencies, we have a very strong magnet that is 12.5 Tesla, which is 200,000 times the magnetic field of the Earth. So the advantage of high power, high frequencies, and strong magnetic field means we can measure very rapidly decaying spins in a protein that hasn't been studied otherwise. So this is the accelerator where electrons come out of, and they go through here. They wiggle through this array of magnets that causes them to be excited, and then they emit light. And that laser pulse is then piped into our lab where we use for ESR experiments. So in order to study a sample, we put it in our magnet. This is our 12.5 Tesla magnet in our lab. Looking at a schematic, we have the free electron laser pulse coming in. Our sample sits right halfway through the magnet right here. And then we have ESR signal that comes out to the detector, which is just, again, the signal of the spins coming back up to their upright position. However, one problem with this experiment is that we have leaked free electron laser pulse that causes signal loss. So here is something called free induction decay, which is a graph of the spin coming back up. So we have time right here and then signal. But you can see here that we have to wait 80 nanoseconds to turn on our detector, because in those first 80 nanoseconds, we have too much interference from the leaked free electron laser pulse. So one solution to this is using something called a cone absorber, which you can see in this picture. This is an ESR setup at a different university, the University of St. Andrews. However, these cones are very expensive. They're $2,000 a piece, and if you count in this picture, they're over 20, so the cost adds up very quickly. And you can also see that they're very big and bulky. They're over a foot long. So here's our ESR setup. This is the optics table that our free electron laser pulse comes through. And we have one cone way back there, but you can see that there's not enough room for cones to absorb in various places on our optics setup. So it's my goal to make something that is cheaper and something more compact to fit on our optics setup. So the cone absorbers are very good at absorbing. We can measure reflectance by taking a ratio of the power of reflected light back versus the power in the background. And for the cones, it's 1 in 100,000. So that's very good. And these cones absorb at all frequencies of light. So it's my job to design new terahertz absorbers with water. So the idea is that the water will absorb any of the light that's scattered. We want to be able to tune these absorbers to absorb exactly at 240 gigahertz, which is the frequency we run at. We don't want any reflected light, obviously, and these should be watertight because we don't want any water leaking on our optics table. So in order to do this, we use something called a thin film interference technique. So you have three mediums: air, a plastic coating, and water. So light hits the first surface coming in from air on the plastic coating. Some of that light will continue on and hit the water, and then some of that light will continue on, and any of that light is absorbed by the water because water is a very good absorber at this frequency. However, some of the light will reflect off the first surface, and some of the light will reflect off the second surface. But we want to choose a plastic that has an index of refraction and thickness such that we get destructive interference so that there isn't any light reflected back. So in order to make these absorbers, I sketched them in a CAD program, and based on our theoretical calculations, our plastics we're using are mylar and plexiglas, and then DI water for the water. So right above there is a 10 centimeter long by about 2 centimeter tall absorber, so very compact compared to the cone absorber. And then the actual holder of the water will also be made of plexiglas, so I took that to the machine shop and milled it on a mill. So here are a couple of the absorbers I made. The one on the right there is the 10 centimeter one, the one that's more compact for our ASR experiments. I made a bigger one with a 10 centimeter diameter for testing purposes, so we can make sure that when we're measuring reflectance, the beam is hitting the center of our absorber. So in order to test these absorbers, we use something called a vector network analyzer, which sweeps a range of frequencies of light so that we can test or measure the reflectance. So really simply put, we have the VNA and a power source that emits the light. Light waves come and hit our sample, which in my case is the absorber. So in this picture, here's the VNA, and the absorber is mounted right there. So we first tested a mylar plastic film, and we got a reflectance of 1 in 100. So remember, the cone was 1 in 100,000, so this isn't exactly as great as we would want it to be. We tried plexiglas, and we got 1 in 1,000, which is actually pretty great. It compares pretty well to other absorbers. So that's great, but we see that it absorbs really well at 230 gigahertz, where we want it to absorb at 240. Another problem is that the absorber I made wasn't uniform. You can see all the different colors, so based on where I had the absorber mounted on the VNA, the absorption would differ a little bit, so it's all around 230, but it differs based on whether the beam was hitting the bottom, the top, or the center. So in order to continue on with making new absorbers, I'm going to tune the plexiglass thickness so that it absorbs at 240 gigahertz, so that big peak moves over to 240 gigahertz. And then also try different plastics that are similar in index of refraction to mylar and plexiglass to see if we can get a greater reflection or greater absorbance closer to the cone that was 1 in 100,000. So I'd like to thank my mentor, Devin Edwards, Andrew Pierce, who helped out with the VNA, my PI, Dr. Mark Sherwin, Eric Lubin, and Kevin Moore with UC Thank you.